So thank you for having me, first of all. Good to see such amazing numbers of people showing up today. Like the introduction hopefully said, I'm Niels HAGOORT. I'm based in the Netherlands, so not that far away, Peba, which I believe means lower lands. I just learned that. And in my role at VMware, I am covering basically everything vSphere ESXi. Now that is an interesting topic because everybody thinks that's a commodity, right? ESXi, everybody knows it, everybody uses it, hopefully, in this room. But there's a lot of development going on in that space alone. So I want to touch a little bit about where we came from, so where we are today, and some of the future things that are coming up. So the first time I actually came into touch with vSphere ESX back in the day was when we were doing stuff similar like this. And this was basically how we did things back then, right? So I was working for a large ISP in the Netherlands. And whenever we needed to spin up a web server, application server, database server, we had this one-to-one relationship. So we would actually build per customer a dedicated host. And the 4 rack units, so you can imagine power consumption was off the charts. We had a data center footprint that is probably close to Amazon's data center footprint nowadays. Not really, but it was pretty big. So along came my IT director back in the days, and I'm talking like 10, 15 years ago, that he noticed a product called vSphere ESX back in the day, 3.5, I believe. So now, and I hope you can enjoy, that you like the retro slides that I dug up somewhere. Now we had this whole technique of abstraction. So we could actually host multiple servers on one physical box. Thinking about that, that's still pretty amazing to me. And what if we had multiple hosts, right? We could actually have some pooling together. So we now have multiple ESX hosts running virtual machines, and we were now introduced to features like vSphere HA, like DRS, like vMotion, stuff that we sort of take for granted maybe today. But back in that day, that was mind-blowing. Talking about mind-blowing, by show of hands, and it's an easy question, I guess, who remembers their first vMotion? Ah, there you go, Eric. Love the enthusiasm. So again, this is a feature that we take for granted, in my opinion. So I just wrote a blog series about this, and just to give you a little bit more insight of what is happening on the background with vMotion. And to migrate an active state of a virtual machine to another physical host, even maybe a physical data center, that's still awesome to me. And eventually we had this consolidation ratio, which was far more efficient, right? And you know, you all know this. We do that every day. And we kind of lived this phrase. So abstract, pool, and automate. Now we won't go into the automate bit in this presentation, but the abstraction layer, it's really interesting to see what we did on that aspect. Not only from a compute perspective, but we are now also doing that for storage with vSAN, right? We're now also doing that with networking with the NSX family. Really cool stuff going on. And as a side effect to virtualization, it's kind of cool to think a little bit about the environment as well. So we had this report made up, I believe, in 2018 already. And through virtualization, we shrunk emissions. So we avoided, and not we, but our customers, our partners, we avoided 84 million metric ton of carbon dioxide, which is pretty cool if you think about that as a side effect of virtualization, right? But enough of the past. We all know what we did and what ESX brought to the table, basically. Where we are today is vSphere 6.7 Update 3. We just recently released that release prior to VMworld. And 6.7 was pretty much, I would say, a major release. There's a lot of stuff going on there from perspectives of machine learning, artificial intelligence, and how to host those workloads on vSphere ESXi. So there's a couple of highlights that we will discuss in this presentation briefly. And the other thing I want to empathize is if you look at 6.7 and how we release versions today, it's really good to understand that today it's not only about bug fixes, about patches, about security fixes, right? Whenever we release an update, it's also about new experiences, new features that we bring along in those releases. So that's really important to understand. And I'll give you some examples along the way. So first of all, I think, so by show of hands, who is already running on vSphere 6.7? Okay, that's good to see, but still, we have some work on that area, right? Because we've heard you, and I know when I was working with customers that it can be a bit of a hassle to actually migrate or upgrade your environment to the latest versions, right? So luckily, we did introduce some new features that could help you with that. First of all, as of 6.7, we now have a single reboot upgrade, and that helps because that used to be at least two reboots. And a reboot doesn't seem like that challenging, right? But think about how hosts are set up today. So we have hosts with maybe 1 terabyte of RAM today. It's pretty much becoming a commodity already. So a lot of consolidation, large hosts. And whenever you reboot a host, it'll go into hardware checks, memory ECC checks, etc. I've seen hosts, depending on make and model, obviously, and configuration, that could take up easily 10, 50 minutes for one power cycle. Now think about that on scale. So what if you have 50 hosts, right? What if you have 100 hosts? This is becoming a problem. So single reboot upgrades help. The other thing I wanted to point out quickly is Quick Boot. Now, Quick Boot is an interesting technology, an interesting feature, and it is something that we can enable within within VUM, the vSphere Update Manager. So, Quick Boot basically allows us to reboot the VM kernel itself, not the physical box. Now, that helps from a time perspective, right? So, we do have some prerequisites for that. We have you need supported hardware. So we have the vSphere compatibility list, the hardware compatibility list, which you can check. But we also today ship this script that is that check script whether your host is actually supported for Quick Boot. So that might help. Today we only support native drivers, and the VMK Linux driver stack that is basically older hardware is going away in the next major release. That's deprecated. And secure boot is not supported today, but that's something we're working on. So just to give you a quick example of how that looks, on the right-hand side, you'll see a physical box that is completely rebooted. On the left-hand side, you see Quick Boot. So Quick Boot is only about restarting the kernel and is done, right? And on the right-hand side, it's still booting. Obviously, this is time-forwarded, this short video, but it gives you an idea of what is happening with Quick Boot. So the right-hand side is finally done. There we are. But think about what we are doing think about this when you're using large hosts, right? It could take forever, and this could really minimize maintenance windows for you. But it's not only about new patches, not only about new features, it's also about performance as well. So if we take a look at 6.5 and 6.7 vSphere, we doubled the number of vCenter operations that we're capable of doing at one given time. So that's a really important aspect as well. And we do that, again, at the reduction of memory for the vCenter appliance itself. So all things, it's good to know that we are bringing more and more features with each and every update release as well. And it's all about having a platform that is pretty much capable of running any workload. So we do see a lot of traction in the machine learning space, right, in the artificial intelligence space. So I want to talk a little bit about our universal application platform. So this is basically hardware accelerations and what we support in vSphere today that you can utilize to pretty much have a comparable performance to just your bare metal hosts. Because we talked a little bit about the past, right, with vSphere ESXi, and we had all these discussions with the business, with people that we were moving away from bare metal boxes to virtualized instances. Now, we sort of have the same discussion with data scientists, for example, running a high-performance computing platform, for example, those guys are still pretty much attached to their monolith applications, their bare metal instances, and we are trying to change that. So, like I said, the target workloads here are big data, HPC, machine learning, deep learning, artificial intelligence, in-memory databases, you name it. And we have quite some new features with 6.7 to support hardware accelerations to support those workloads. Let's first start off with something I think is a really cool topic, GPUs. Now, everybody knows GPUs from their gaming experiences, right? So it's all about 3D accelerating graphics. But today, we see a lot of GPUs coming on the market for general purpose GPUs, as they call them. So it's all not about 3D acceleration anymore. It's about computations, doing computations in parallel. And we'll talk a little bit about what parallelism actually means. Now, like I said, this is really beneficial to machine learning workloads, to artificial intelligence, to deep learning, which is all basically sort of the same kind of workload. But why really use a GPU for that? Because we already have a CPU in our box, right? And CPU packages are not that inexpensive. Those are expensive. GPUs are expensive. So why would you need those? And it is really a question about latency versus throughput, if you think about it. So high level, if you look at a CPU and compare it to a GPU from a core perspective, this is sort of what you see. So you have a CPU, depending on make and model, and you will go up to, what, 32 cores, maybe? We just saw the AMD launch of the Rome EPYC processors, which will go beyond that. But if you compare that with a flagship offering from NVIDIA, for example, the Tesla V100, you are talking in the excess of 5,000 cores already. So that's one difference. But the latency sensitivity and the optimization in the CPU, that is also about its memory architecture. So if you look at the really high-level CPU architecture, this is sort of what is happening. So you have cores, right? An X number of cores. And you have your level 1 data cache and your level 2 data cache, which is dedicated per core. So this is all about the CPU wanting the data. Oh, skipping too much. This is all about the CPU having its data as close as possible to the core because of that low latency. Because the CPU, whenever we schedule with our CPU scheduler in vSphere ESXi kernel, it's always scheduled against a core, just one core. Obviously, we can have multiple vCPUs configured in one VM, but we are scheduling per core. So keeping the data as close as possible to the core is beneficial. So whenever data is not residing in those layers, it will reach out to the level 3 cache or the last level cache. And even if data is not residing in there, it will reach out, call out the system agent, the memory controller, and fetch data from global memory. But it's all about having that data as close as possible to that core. Now, if you compare that with a GPU, for example, we see another approach. And this is, again, a high-level overview of a GPU architecture. And what we see is that we have a level 1 cache. So we have processing clusters. We have streaming multiprocessing clusters in those processor clusters. And a level 1 cache that is shared amongst multiple cores. And we have a complete shared level 2 cache. So looking at the GPU architecture, it is somewhat tolerant of memory latency. And that is all because we want to keep the cores as busy as possible, if you will. Because remember I said the CPU we are scheduling against a core. So that's a sequential way of computations. Okay, so it's doing computation, it will create an interrupt or whatever, and it will go on to the next one. Now with the GPU, we are scheduling against a processor cluster. So now you have your machine learning workload, for example, your machine learning application that is scheduled against X number of cores in the excess of thousands again. So this is the throughput bit, right? So it's latency versus throughput, and this is parallelism. Now, why is parallelism and GPU needed for machine learning workloads? Now, this is just an example of what is happening in a deep neural network, which is used for machine learning, deep learning. And what you see, let me see if this works. It does, nice. What we see here on the left-hand side is basically the input values. And on the right-hand side, we have the output values. And everything in between is called a neural node, or a network node within a neural network. Now, this is just an example. It can be millions of these. And when we have calculations, computations that are done against graphics, against text data, against voice data, everything machine learning that is going on, this is basically what is happening in each and every node. So this is just a math example. So you have the input values, you have the weight values that are, well, that's going a little bit into detail, again, a little bit too fast. But the important thing here is that there's complex math going on within each and every node. And we're talking millions of nodes, and those are scheduled against the GPU, right? And just to give you an example, what it looks like in a more easy way to understand or consume maybe, is that we have a tensor RT flow application, and we ran it against a Skylake CPU, right? So what you see here is it's image recognition of flowers, and you see that it's basically sequentially going through all the images, not really fast. If you look at the lower hand side, we have images per second around 4, right? Now, if you schedule this against a GPU, for example, this is how it looks like on a GPU. Right? So we have parallelism and a lot more going on at a given time. So we are now processing images per second, almost 900. So this is basically why we need a GPU for machine learning workloads, for artificial intelligence. Now we have multiple ways of consuming a GPU and attaching it, basically exposing it to a virtual machine. So we have the ability to have one full GPU, just a PCIe device, to one VM. And we can do that with direct path I/O or with NVIDIA vGPU. We can have multiple GPUs used by one VM if you really need that insane amount of computation power. But hey, if your data scientist says he would actually need this, we can do so. And we can do that with direct path I/O again, vSphere with Bitfusion, and NVIDIA vGPU. Now, the last option, NVIDIA vGPU and multiple GPUs for one VM, that is actually something that we only released in 6.7 update 3, so in the latest release. But the sweet spot is probably this option, and this is something that we're doing with compute resources as well, right? So we are carving up hardware resources, like a CPU, but in this case a GPU, and basically let multiple VMs use that one PCIe device. Now we can do that with Bitfusion again and with NVIDIA vGPU. Now let's dig a little bit deeper in all those options, because direct path I/O, that's a feature that's been that's around for a long time, right? But it comes with a lot of constraints, a lot of restrictions from a vSphere feature perspective. So HA, DRS, those are all not usable with direct path I/O, because what we are doing, we are basically configuring a hardware address of a PCIe device to the virtual machine and the guest running inside the virtual machine. So obviously we cannot move that VM around because that hardware address will mismatch on a destination host. Now this is somewhat of a technology preview. It's something we're thinking about doing in the future release of vSphere ESXi. And that is basically to have a capability mapping in between. So we would now configure that VM with the capability of a GPU. And that layer, that new layer, that capability mapping, will actually map that to a hardware address. So this would allow some improvement on initial placement, for example, but also about vSphere HA. So what we used to do, and we are doing today with direct path I/O, is basically the whole left-hand side. So a lot of manual provisioning going on, and it's not really flexible from a portability point of view. Now on the right-hand side, again, stuff we are thinking about doing is have DRS and hardware acceleration awareness. So we would configure, like I said, that VM with a specific capability, a GPU, maybe also include the model as well. So maybe a GPU and a model of a V100 Tesla from NVIDIA, provision that VM like we do always, power it on, and DRS will take care of the rest. It will find a host with a device that is available. It will assign that device to the VM and power it on. Now, this is really important from an availability perspective if you think about vSphere HA as well, right? Because whenever vSphere HA now kicks in, it will probably be able, obviously depending on the configuration of your cluster and your hardware, to spin up that VM on a surviving host. Moving on to Bitfusion FlexDirect. Now, by show of hands, who has known about Bitfusion? Ah, we have one. Cool. So this is Bitfusion is an acquisition that we recently did, and it is a really cool, interesting technology because it's about remoting CUDA. And CUDA and OpenCL, the Open Computing Language, is basically ways, frameworks that machine learning jobs use to fire off computations to a GPU or a FPGA for that matter. Now, what Bitfusion brings to the table is that we could have client VMs running on ESXi hosts that are not equipped with a GPU, and they will connect over a fabric to an ESXi that is configured with a GPU in this example. So that GPU on the server side, on the lower side, must be attached to that virtual machine, right? That Bitfusion FlexDirect server VM. Now again, we can do that using DirectPath I/O, but we also support NVIDIA vGPU for that matter. And a lot of questions arise with customers because you're now going over a fabric, which could be your default TCP/IP stack, just your Ethernet network. We also support RDMA. We'll talk a little bit about RDMA later on. But it's machine learning. So it's basically firing off the job to the server VM, which is equipped with a GPU. The computations will be done on that server VM, and the results are copied back to the client VM. And like I said, it's a recent acquisition, so we are looking how to incorporate this in the vSphere ESXi stack as well. But cool technology that is coming up. So the last option we had is the NVIDIA virtual GPU. The diagram still says grid. We do have some other licensing models. Well, not we, but NVIDIA. What it really is that you would need a NVIDIA vGPU supported GPU device, obviously, in your host. On the ESXi level, you would install a kernel module, a VIP. Now this introduces a new layer of scheduling, specifically for the GPU, like we are doing with CPUs, for example. So now the guest that's running inside the VM would have the CUDA and the driver for that vGPU, and we can carve up that physical PCIe device, that physical GPU, and attach a VM to certain amount of cores, certain amount of shares, certain amount of memory on that GPU. So it's a really versatile and flexible solution as well. And we created this together with NVIDIA, right? Because we actually have engineering on both sides working closely together to come up with these solutions. And what we did as of 6.7 is that we already had some portability options with NVIDIA vGPU. So we could now suspend the VM, move it to another host, obviously equipped with a GPU from NVIDIA as well, and we could now resume that VM. Now that helps, right? That's basically mitigating the risk that we have with DirectPath I/O today. But as of 6.7 update 1, we also included vMotion support for that. And what is not in the slide, because whenever you are running 6.7 update 1 and you perform a vMotion with vGPU enabled VM, you would have a stun time of a couple of seconds, maybe. Now we trimmed that down quite extensively in update 3, just to show you that there's a lot of development going on in this space. Talking about that, if you look at the 6.7 update 1, update 3 release, it's a constant movement and a constant evolving partnership that we have with NVIDIA in this specific case. So if you want to leverage vGPU or GPUs in general, it would be really beneficial for you to run the latest vSphere version. Now moving on to FPGAs. So do we have anyone in the audience who is familiar with FPGAs? Anyone? We have some. because it's a technology that is used in industrial automation for ages already. But it's now finding its way to the data center as well. And what it really is it's, in this specific case, a PCIe device, and it allows you to design a digital circuit. And we compile that digital circuit, which is called by FPGA developers synthesizing, into a configuration, a bit file, and we put that on the FPGA. And now the FPGA, the hardware device, actually just behaves like the digital circuit you just designed. Now this is still pretty new, so we see a lot of interest in this, especially from the telco NFV side of things, for example, because this specific card, and I'll show you in a bit, has an architecture that is also allowing you to remotely call out that FPGA over a network fabric, over RDMA, for example. So looking a little bit closer in the FPGA architecture and this specific Intel card is that you have the FPGA chip itself, right? And a number of logic elements. Now, you are constrained by the number of logic elements in designing your digital circuit, but it is quite substantial today. And we have multiple interfaces. So obviously, in this case, it's a PCIe card, so it's connected directly to that host. But like I said, it's also shipped, this model, with a QSFP plus. So you could have a 40 gig connection to it, or 4 times 10 gig. Really cool, interesting stuff. And as of 6.7 update 1, we introduced support for the Intel Area 10 GX card. Today, we are leveraging that technology and exposing it to the VM using direct path I/O. Cool thing is that we can also use these FPGAs with BitFusion as well, because BitFusion is not only about GPUs, it can leverage FPGAs as well. All right, enough about FPGA. Like I said, it's an emerging technology, and it's finding its way in the data center. It's good to know that we already support some models. Now, talking about NVDIMM, or persistent memory, for example. Really interesting tech as well, as it introduces a new tier of storage for enterprise applications. So we used to have the magnetic disk. We all are all familiar with that. We have flash media, SSDs, NVMe flash drives, you name it. You have DRAM, your global memory in your system. You have some caching involved. We discussed that earlier on, and the CPU on top of it. Now, persistent memory, or NVDIMM, basically sits in between flash media and DRAM. And it is all about high durability, lower power consumption, but the most beautiful thing about it is the performance numbers from a latency perspective, from an access time perspective, and it is byte addressable. Now, that means that you can basically use NVDIMM, or persistent memory, as you do with global memory. So it's just puts and gets to the memory modules, but it is persistent, so it survives host reboots. Whenever you put data on a persistent memory or NVDIMM device module, which is basically just looks like your typical DRAM chip, right? And whenever a host power cycles, that data is residing on the persistent memory module still. So from a performance perspective, if you look at access times, this is basically what we had with the flash media and flash storage that we, or the storage media that we have today. Now, looking at DRAM, you see that we are talking 30 to 100 nanoseconds for access times. Now, persistent memory sits really close to DRAM with 50 to 300 nanoseconds. So that's insane performance that you get from such a memory module, persistent memory module. So we see this whole new paradigm shift in application design. Because if you look at, for example, in-memory databases, right? We have SAP HANA, we have Oracle solutions. And today, customers are buying a lot of DRAM to support those solutions when running in-memory databases. Now, persistent memory sort of fills in that gap because it's fast, it's non-volatile, and it's inexpensive. Well, inexpensive if you compare it to DRAM, because it can still consume quite a lot of budget. But it's a cool option to have basically in between storage media and DRAM. Now, if you have PMEM modules in your system, we expose it like this. So you just see your global memory, like we are used to having, and we introduced this new bit, which is persistent memory. Now we have multiple ways to expose this to the virtual machine as well. So one option is the vPMEM disk, which is basically just a data store like we have on block devices today, on your SAN, on vSAN as well. Just putting VMDKs on persistent memory. Now you will benefit from a lot higher performance, but you are still bound to the SCSI or the NVMe stack. We also have an option to have it virtual PMEM aware, or just via virtual PMEM. Well, basically that is the operating system within a virtual machine and the application running inside of it, and either of them being aware of persistent memory. Now you can use it as a byte addressable device. So like I mentioned, just like typical DRAM, so puts and gets from the memory modules, but the data resides on those modules. Now this is what that looks like from a high level perspective. So you have the virtual disk, like we all know today. We have the SCSI and the NVMe stack, and you will basically have a data store running or hosting those VMDKs. Now with virtual PMEM disk, you still have the same SCSI NVMe stack, but you will have that persistent memory module in which you can still host the VMDKs. Now the sweet spot is what we just discussed, the virtual PMEM. Now it will expose that as NVDIMM to the virtual machine. So whenever you use that, we have this Oracle test bed in our lab. We can actually now have, on the right-hand side, you see the highlight, an NVDIMM controller connected to that virtual machine. So now we use it as a byte addressable device and have that insane low latency and persistency in those modules. So again, really cool tech, and this is all happening today, right? This is, you can utilize it in the latest 6.7 releases already. So, and we already briefly touched upon RDMA, which stands for Remote Direct Memory Access. Now again, really cool tech, and it's been around for a couple of years, but we don't really see it back coming in the data center just yet. We have some early adopters like Eric Bussing here in the audience. What it means is that we now have a way to bypass the TCP/IP stack. So with increasing bandwidth that we see today, we have 25, we have 40 gig, we even have 100 gig already, right? And using the TCP/IP stack and to fully saturate such bandwidth, we would use a lot of CPU power to actually be able to transmit data on those networks. So this is something that RDMA solves as well. Because on the left-hand side, you will see a user space sockets API, just your regular application virtual machine using the sockets, the TCP stack, IPv4, all the way down to the network device, which is basically your NIC. But it is all kernel, it's all consuming CPU cycles to actually put those, to transmit that data and put it on the wire. Now with RDMA, we use something that's called the verbs API. And whenever a control path is set up between multiple hosts, we completely bypass the kernel, basically saving up a lot of CPU cycles. Now, you see on the lower end side that we would require a host channel adapter, which is basically just a NIC that is RDMA capable. And today we support a high transport network. We have InfiniBand, right? We have Rocky, we have iWarp. The beautiful thing about Rocky, which is RDMA over converged Ethernet, is that you can utilize your Ethernet backplane. So your Ethernet fabric. With InfiniBand, which is an awesome technology as well, you would still need to have a separate fabric, like with Fiber Channel, for example. So what does that look like in the real life scenario maybe? Is that we have multiple ESXi hosts that have a control path set up. So basically, they are able to communicate to each other's memory. So this is what RDMA does, right? It talks to a remote host and directly looks into its memory. Again, really high bandwidth, really low latency, but we do have some requirements for this to actually be happening on ESXi. And first of all, we need a NIC that supports RDMA. So we have this ESXi command, and this is one of our lab hosts that is equipped with a ConnectX-4, and it's directly connected, so we don't have actually 100 gig switches in our lab at least, but it is cool tech. And we see that we now have an RDMA capable NIC in the host. So the following options we have is Rocky version 1 or Rocky version 2. You will see that in the UI in a bit. And this is all about basically comparing to Ethernet networks, TCP/IP stack layer 2 network. That's so a switched network. That is basically where Rocky version 1 comes into play. If you have a routed network, routed Ethernet fabric, then you would use version 2. And the only thing that we need from an Ethernet fabric perspective is we need priority flow control. So that's something to keep in mind. But RDMA, if you have a NIC that is capable of doing RDMA, we can connect it again using direct path I/O. But we want vMotion, we want some portability. So we introduced the para-virtual RDMA adapter. And that aims to solve the complications that we have with direct path I/O, right? And we have that available as of VM version hardware version 13 already. So that's 6.5 if I remember correctly. And it's only available for a Linux guest OS today. But if you have such a VM, you can now configure a para-virtual RDMA adapter and choose that device protocol we just talked about. And this is borrowed from Mellanox. But we did a test on a para-virtual RDMA adapter. It is using an Ethernet fabric, obviously. And this is just a bandwidth test, right? Just to try to maximize that bandwidth on an RDMA network. And what we see is that we could easily saturate, or almost saturate, a 100 gig NIC with para-virtual RDMA. Now, sadly, the most interesting metric is not on this slide, which is the CPU cycle spent for this, but it was low. It was, if you want to do similar bandwidth with the TCP/IP stack, you would consume a lot of CPU cores just to be able to transmit those packages. Now, the key takeaways of all these hardware accelerations is knowing that vSphere really now is a universal application platform. We are evolving. We see a lot of hardware technologies moving around and evolving as well. So if you really want to benefit from the fullest, you would need to upgrade your vSphere stack. So this all is happening today, right? Let's talk a little bit about some of the things we are thinking about doing for the upcoming future. And one of the things that we are working on is ESXi for ARM, which is really cool tech again. And if you saw the VMworld keynote last year by Ray O'Farrell, I actually included the short URL, which will take you to the YouTube video on the exact second where he is demoing ESXi for ARM. And he demoed a scenario where we had windmills, and windmills running a critical workload inside of it. So that windmill had 2 ARM hosts, right? And we used fault tolerance for that workload running on those 2 hosts to basically have that availability guaranteed between the 2 hosts. And we were able to use vMotion as well. Now this all sounds like, well, pretty easy to do with your regular data center, your x86 host, right? But we are talking ARM. ARM is a completely different architecture for us to develop ESXi against. So the thing what we are trying to do is that we have operational consistency. So we see this whole movement on edge, on and ARM devices in general because of the power consumption of an ARM device, but mainly the cost involved, right? The ARM architecture is way more cost efficient than you would with a x86 host, especially on the edge, because you don't want to use a full-size data center on each and every location. For example, windmills, but you name it. There's a lot of examples out there. We want ARM, but we also want to have that operational consistency. So whether you are using ESXi for ARM or ESXi just on your regular x86 host, we want to have the same look and feel basically. So we do have a single pane of glass. We do have ARM ESXi host already tested out, and it's a really cool development to see what is going on. And we already have that support for vSphere features like vMotion, like DRS, like HA. And we also have some other really cool applications for ARM as well. So this was just a test. We had a witness node, a vSAN witness node. So a stretch cluster running on top of just your regular x86 hosts. and the witness node itself was placed on the ARM host. Now, I just mentioned that we are looking to have the same look and feel, right? The operational consistency. And that is exactly what we're doing, because we now have one vCenter instance, which has a cluster for the ARM device, and has the same cluster for, or has a cluster configured for the vSAN stretch cluster itself. So this is just one thing we are playing with, and where we see a lot of possibilities for ARM. One other thing that I want to mention, and this is again a tech preview, because this is in development, and we are thinking about doing, is having ESXi for ARM running on Graviton. Now Graviton is basically, you can compare it to VMC on AWS, right? So we have bare metal instances that we get from the Amazon data centers, and we are putting ESXi on top of that. We can now, with Graviton, we are thinking about doing the same for ARM as well. So you can now spin up ARM on Amazon hardware. Now this is actually, we have a dedicated team working on ESXi for ARM, and they are looking for early validation proof of concepts. So if you think that you have a really cool use case for this, I would be happy to talk to you and put you into contact with that specific team. But that's just, that we were talking Amazon hardware, right? Whenever I talk to customers and ESXi for ARM is mentioned, basically what we are saying is, okay, how can I run this on a Raspberry Pi? And we can. So this is just a test we had. We run a Raspberry Pi 3B, which consists of 1 gig of memory, and we sort of created a subset of ESXi. So that's basically all the kernel modules that we require, some USB and networking support, but that's it. So no VPXD, so no vCenter integration. But we were able to trim the memory footprint of ESXi down to 400 megs, around 400 megs. So that would still leave like 400, 500 megs for actual VM to consume and run on top of that ESXi, top of that Raspberry Pi. So what you see in the middle is actually a tiny Linux VM running on a Raspberry Pi. Now, let me stress that this is just a showcasing, right? We don't really see a big traction going on and running ESXi on Pis. So you have a data center full of Pis and run ESXi on top of them, which would be cool, but it's just to showcase what we can do with devices. Because when we look at ARM devices and what is happening, we see just your typical rack server, for example. So we had this Ampere Lenovo box, which is just a rack server equipped with ARM processors and some local media as well. So that's a cool, interesting thing. But we also see edge CPE devices. So this could be a cloudlet, this could be an NFV device, you name it. Everything that runs a ARM processor, we can run ESXi on top of that. So another cool thing I would like to highlight is the HiveCell solution. And this is basically just stackable nodes, literally, because you can stack them on top of each other. And I know one of our CTOs, Chris Wolf, is actually showcasing this, or did showcase this in the Boston VMUG, I believe, just yesterday. And another thing he showcased, and that is something that I find particularly interesting, is hardware accelerations with ARM processors running on top of them, or inside of them. So this is a SmartNIC, and the actual image is of a Mellanox Connect X5 card with a Bluefield SoC, a system on chip. So they have a model in which you have an ARM processor running 8 cores and up to 16 gig of memory on a PCIe device, right? So we could use ESXi running on a PCIe device, and we could now also have multiple SmartNICs in one host. So the ESXi and ARM team actually tested this. So it's containing a Connect X4 from Mellanox. It's also a Broadcom and another vendor. So they had basically one host that is equipped with four ESXi instances, because the SmartNICs would run ESXi and the host itself as well. So there's no nesting involved. Really cool and interesting tech. And this is something, the SmartNICs especially, is maybe a way that we can offload network function virtualization to those SmartNICs, but still be able to manage them through vCenter, right? So we only scratched the surface here. There's a lot going on in the ARM space. Enough about ARM. The last thing I wanted to touch base upon, because we're running out of time, is what we announced at VMworld San Francisco. And this is basically Tanzu and Project Pacific. Now, there is some misconfusion how to both basically work together. But Tanzu is basically the mission control, the all overlaying architecture for building, running, and managing cloud-native applications, for example. So we have Pivotal, we have a lot of things going on in the build area. And in the run area, we would see PKS, but also Project Pacific. Now, Project Pacific itself is really interesting because we are now re-architecturing vSphere itself, vSphere ESXi, to incorporate Kubernetes into the vSphere stack. So whenever you want to spin up a Kubernetes platform, you would now be able to do that within vCenter. Again, this was just an announcement. We are planning on releasing this in future releases. But I do want to stress, if you are going to VMworld Barcelona, there's a lot of cool sessions on Project Pacific. On the vSphere blogs itself, we also have Kit Colbert and his team blogging a lot about Project Pacific. So if you want to know more, please look out for those blogs. And in the end, this is what we talked about, right? High performance computing, so machine learning, etc. ARM, Kubernetes. It's all running on vSphere ESXi. So it's not a commodity. We're constantly developing ESXi to host all the applications. I included some links on the top, especially the vSphere blogs as well. Utilize that to know everything about Tanzu, about Project Pacific. And with that, I would like to thank you for your time. If you have any questions, hit me up. I'll be around for a couple of hours. Thank you.